today we're going to do section 2.6. So first, let's scan the book. Let's see, let's keep it parallel somewhat, a little bit closer. Okay, that's about it. All right, and this page, we've already scanned it earlier. So, but I guess I'll just do it again because we only have 2 pages this time. And the next 2 pages, and that's about it. Let's see, let me line this up. Is that good? This way, okay. And yeah, that should be it. And then zoom in a bit on the top. And then a bit on the bottom. Okay, so that's that. Now today we are going to talk about invariants, which what that means is that we are going to move the axis of reference, okay? And the first way we're going to move it is the normal axis, which is the XYZ axis, is where it is. But what we're going to do, the first thing we're going to do is called translation. That is, we're going to move it without turning, okay? But move it to a different spot like this, okay? All 3 axes point the same, but we are going to move it like that. Now, in that case, a vector doesn't change at all, okay? Because a vector is only defined by its magnitude and its direction. We don't care where it is. That's always how we understand it. And therefore, the vectors don't change just because your coordinate system got moved. And so please read the details of that, okay? From the beginning of the section all the way down to here, where it talks about called the translation. See, the translation? Translation for vectors is a piece of cake because nothing's different. Okay, your vector is exactly the same one, no matter how much you translate your axis. The next question is more concerning. That is, what happens if we have a rotation? That is, your axis, your XYZ axis, okay, now it's going to do this. It turned right on it's still at the origin, but it turned in some crazy way, okay? It can turn any old angle. So anyway, your axis turned. What happens? Well, if your axis turns, then what happened to your vectors? That is what we're going to explore. So I scanned the book into my Kindle so that I can explain it a little better, because then I made a little bit of editing and also draw some pictures, because your book doesn't have any pictures, and I feel that it's easier for me to explain. So look at this first picture. We have alpha, beta, gamma. What are they? They are unit vectors who are all perpendicular to each other such that each of them has the length of 1. Well, they are unit vectors, right? And more importantly, alpha is beta cross gamma in that order, which means if you swing your hand from alpha to beta, your thumb is going to point at gamma. In other words, this follows the right-hand system. And as a result of that, the other 2 cross product is also true. That is, beta then is equal to alpha cross gamma cross alpha, okay, following the right-hand system. And that's because they're mutually perpendicular. So all this stuff works out. And remember, this thing is equal to, and each one of these things have the length of 1. So they are just tiny little things here. All right, so next, let's consider alpha itself. Now I'm going to create, see, alpha, beta, and gamma are still like it was in the first picture, except that this time I'm going to draw 3 axes right along them. That is, alpha will define the new x1. We'll call it x1 prime, okay? And the beta will be the new x2 direction. And then gamma will be the new x3. And so alpha is 1 unit distance from the origin in the positive x1's prime direction and has coordinates alpha 1, alpha 2, alpha 3 in the old system, okay? So alpha 1, alpha 2, alpha 3 is what it used to be called. And now it's just called, in the new system, in the new system, it's just called alpha 0, 0, okay? But we won't worry about that right now. So in the old system, that is in the where originally alpha is called alpha 1, alpha 2, alpha 3 is a unit vector. All right, so next let's do one more thing. Now my picture is still the same. Okay, this is exactly the same picture as we saw earlier, that one, except I drew one more thing on there, and that is the point P. P is some point with coordinates x1, x2, x3. In other words, P is x, okay, for our argument. I mean, for our discussion here. So anyway, but we call it P, just, well, so that we can understand it better. And so, and then, and P is a point that it will then has a coordinate system with the old one, which is x1, x2, x3, and then it'll have a different bunch of numbers in the new system. Okay, where that is what is, if you pretend that the x1, x2, x3 is the new xyz coordinates, what would the new coordinates of P be? And we're going to calculate that. But first, we're going to calculate the length of P. I mean, the length from the origin to the point P. That, being that P is x, the length is just the magnitude of x, or x dot x square root of x, which I have written right here, okay? L is the length of OP, so then, which is square root of x dot x, okay? Now next, then for x, it says xi, let's start at 1, okay? So x1 prime then that is the coordinate of P along the x1 axis will be L cosine theta 1, as I draw the picture here. I didn't draw the perpendicular line, but you can imagine, okay? It's, in other words, its projection onto the x1 axis will be L cosine theta 1. And similarly, for x2 and x3 will be L cosine theta 2 and theta 3, which I didn't draw, but you can imagine this thing projecting onto x2, that might be the negative side, and x3, which is down here, it will project maybe on the other side, whatever, okay? It will project, the projection will give it its three coordinates in the new axis. So from that, what we get is that, okay, coming from this equation, xi equals to L cosine theta I, that means that xi equal to, well, cosine theta is what is cosine theta 1 right here? And the cosine theta 1 is x dot alpha, okay? And divided by their magnitude, because that is what the angle is called, that is the formula for the cosine is the two vectors that forms the angle, right, divided by magnitude of the two vectors. And the magnitude of alpha is just 1. So all we have to do is divide by just the magnitude of x, we get cosine 1. And we substitute it in here to get the first formula, which is x1 prime is x dot alpha. And similarly, with cosine theta 2 is x dot beta divided by the magnitudes. So x2 prime is x dot beta, and then x prime 3 is x dot gamma. So that is how the principle applies. Now, if this looks slightly confusing, please stare at it until it makes sense. Okay, just look at it for a while until the whole thing comes clear to you. Once you explain it, it's just some basic geometry, really. Yeah, so please make sure that this all comes clear to you. Okay, and then we'll go to the next section. Next, let's look at page 85, section 6.2. We are considering now the invariance of the inner product, that is the cross product, during a rotation. Now, as we have mentioned earlier, the rotation formulas are following this. That is, the new coordinates follow the formula in the old coordinate by dotting alpha, beta, and gamma. Okay, each dot product gives you the new coordinate. So next thing is that we are going to try to prove that our dot s equal to our prime dot s prime. That is, once you've done the transformation, that the dot product should be the same. Well, of course it is, because all you did is rotate it. You haven't changed anything, right? I mean, the thing still looks the same. You just rotated the coordinate system, and the angle between them in particular is the same. Their magnitude hasn't changed. So then our dot s is going to be the same both cases. However, we are now going to give a different proof of this thing that even though it's obvious geometrically, we will give a different proof, an analytical proof with a bunch of symbols. Okay, so that is what we're going to do. And so I scanned it in here so I can edit something to make it easier for me. So then we have, this is what we had before. That is, the new coordinate system is equal to the old one, dot alpha, beta, gamma, respectively, to get the three components of the new system. Now, because of that, then we have R and S. Okay, we have the new ones, the R prime, one prime, which is R dot alpha, just like this one. Similarly, for S, S1 prime is S dot alpha, and etc. Okay, so these are the same. So then what we're going to do is we're going to calculate R prime dot S prime. That, of course, equal to each component being dotted together. And then we'll plug this value up here, down for each component. So we get things like R dot alpha times S dot alpha, the first line, right? And etc. The next thing we're going to notice is that the part that I underline, S dot alpha, alpha is beta cross gamma. So I'm going to plug that in. And so it becomes S dot alpha then becomes S dot beta cross gamma, which can be written in determinant form by some formula back on page 64 that I wrote down on the other side. All right, so then next, let's see, so then R prime dot S prime equals to, we'll put the determinant form down there. And so then it becomes, the red underlined part then becomes S beta gamma, okay? And similarly, the other parts also becomes S gamma alpha and S alpha beta and so on. So that is, so please check this to make sure everything makes sense. And that we will store in our memory as equation 1. So the next part, okay, now we will ignore equation 1 for a little bit and do something completely unrelated. I mean, that looks unrelated. What we're going to do is look at this 4x4 determinant, okay, where the top row is called Si, for I going from 1 to 3. And so let's first consider Si, I equal to 1. So we have S1 in the first row, S1, alpha 1, beta 1, gamma 1. Okay, and the second row, it becomes S1, S2, S3, etc. Now this determinant, as you can see, the first row is going to be equal to the second row, or the third row, or the fourth row. Therefore, this determinant is going to be equal to 0. Okay, and then the next thing we're going to say is that the Si, I can be 1, 2, or 3. We are going to calculate the determinant, which we take positive Si, right, times the determinant of the minor, that is alpha, beta, gamma. That's how you calculate 4x4 determinants. If you're not sure what I'm talking about, please look up, Google how to do the determinants in the 4x4 dimension. But anyways, the same as the other ways, is really tedious. But basically, it will, if you look it up, it will tell you you do calculate determinants by taking Si, okay, times the determinant of alpha, beta, gamma. That is the stuff down there. And then minus the next one, that's alpha I times let's see, alpha I times S beta gamma, and so on, right? This whole thing checks out. So please check that yourself. And then so that is how each one works out. So now this applies for both. For all I equal to 1, 2, or 3, so we can write down S as a vector. Just write down the vector here. And so it works for, if it works for all the components, it also works for the vector themselves. So we write down the vector, so then now we have a vector equation, which is what is given there. All right. So next, we are going to look at, let's see, what is that? Next, we're going to notice that alpha, beta, gamma is what does it equal to? That alpha, beta, gamma itself is equal to, well, remember what, that's a determinant, okay? The determinant is the same as alpha dot beta cross gamma. We mentioned that a little earlier. See, right here, that RST equal to R dot S cross T thing on page 64 on the other corner, right? So we'll use that same trick here, the alpha beta gamma is alpha dot beta cross gamma. And what is beta cross gamma? Beta cross gamma is alpha. Okay, that's how we define these things. And so therefore we can put alpha there, and alpha dot alpha equals to 1 is also how we defined it. So this, in other words, this whole thing is 1. So we can write this equation down without the alpha beta gamma. So we got here. The rest stays the same. Okay, so far so good. Now the next thing we need to do is we're going to dot with R. That is, we'll take the dot product. The entire equation will get the dot product treatment. So we'll take R dot every single thing here, okay? And then of course we get this. And the thing that I underlined in red, we're gonna switch the two things. We'll switch the alpha gamma into gamma alpha, which switches the sign before it, okay? The sign goes from plus or minus because when we switch those things, we're switching the rows. In this case, the columns, but either way, they're the same for determinants. So once we switch it, then it becomes a minus. All right. So now we have R dot S minus those three things equal to 0. So we're going to put those three things on the other side of the equation. Now we have an equation for R dot S. All right. That looks, well, like that. Now all the signs are plus, okay? And then now I'm going to copy and paste equation 1 that we looked at a little bit earlier right down here, okay? This is identical to what I have before, right? What we had before is just, I just copy and pasted it down so you can see it. Now, you compare these two equations on the right side. They are word for word identical, okay? So therefore, the R dot S equals to the new R prime dot S prime. So the dot product is exactly the same under, what are we doing? Rotation, right? The dot product is identical during rotation because, well, for one thing, the dot product is just a number. It's either the same or it isn't. So, so as it turns out, and when you have two vectors, after you rotate them in the same, under the new into the new system, actually the axis is what's rotating here. The vectors didn't move. But as far as they're concerned, they sort of moved. And so anyway, because the world changed, okay? So, but in any case, the dot product stays exactly the same, which is just a scalar value. Now, so that's how we finished the proof that this is a analytic proof of why the dot product doesn't change during a rotation of the axis. And how specifically, I should mention that if you set R equal to S, right, then R and S are the same thing. So R prime dot R prime is just R dot R. Okay, put S into R in this equation. What does that mean? That means the length, which is the square root of R dot R, is the same as the new one. Okay. In other words, the length during a rotation of a vector does not change. The length is invariant. Okay, so that's that. Next, let's look at the next page, page 86. We're considering the invariance of the outer product, which is the cross product. Before we were doing the dot product. I hope I said that right. I wonder if I said the cross product, but I meant the dot product before. Now we are doing the cross product. So the cross product is invariant in the sense that the cross product is just some area, right? And then when you rotate something, the area hasn't changed. So the cross product is invariant in a sense, but we need to be very careful as to understanding what that means exactly. Okay, and so let's do that, and then let's consider this. All right, so I have again written down here. And let's consider the cross product. Now, our cross S is being transformed. Okay, so transformed to something, we'll call it T prime. Then in that case, our cross F being transformed to T prime, then we'll calculate it. That is, by definition, it is our cross, the first component is our cross S dot alpha, okay? And then which can be written as our S alpha by some rule on page 64. Okay, so next, our cross S dot beta, again, same thing, our S beta, and the third one becomes our S gamma. So we'll put that away for a second. And the next thing we're going to do is figure out what our prime and S prime is. During transformation, but based on the definition, R prime Each component will be r dot alpha, r dot beta, etc. And S transformation will be S dot alpha, S dot beta, etc. Okay, and then so those two will be transformed according to the formula we just learned. And then so next we are going to consider what is the situation when the two new transformed objects, what if we cross them? What is R prime cross S prime? So I'll call that U prime. Your book didn't call it U prime, but I feel that calling it U prime might be a little clearer. And so anyway, so I'm calling, so U prime, I'm defining it as R cross S, R prime cross S prime, sorry. And then by definition of what we just did, then the first component of U prime would be, okay, doing cross product here, literally. And so we'll do it downwards, which is the same, you know. The U1 is the I component, which is R2S3 minus R3S2. And we plug in all the values here, okay? Because R2 is R beta, S3 is S gamma right here, and so on. So when you check that out, that is, so I got all three cross products written here. All right, so the next step is to recognize what this thing is. If you look at it carefully, you'll recognize immediately that by Lagrange identity on page 64 is R cross S dot beta cross gamma, the first one. And similarly, the others are also the dot product of some cross product as well. And yeah, so then, well, that's doing pretty good, okay? So that's a bunch of stuff crossed and dotted. What does that mean? So the next thing we are going to consider is the definition of alpha, beta, and gamma. They are like the cross product of each other, right? Specifically, the first one, beta cross gamma, is alpha, so we can stuff that in. And that's U1. And the second one is beta, and the third one is gamma. Okay, so then we can write this thing in the determinant form by that formula on the top right corner over there again. Okay, our cross T dot S dot T is RST. So similarly here, it becomes our RS alpha, the determinant. And then, okay, the second one is RS beta, and the third one is RS gamma. And what are those things? Now, we've seen those things just recently. And if you look up, okay, I got barely enough space to show you. Now, look up, you notice that that's RS alpha is exactly T1 prime. And then, and so on. So these two things, they are exactly the same. And then, so remembering what it is. Now, T1 is transformed from R cross S, whereas U is the result of R prime cross S prime. They need not be the same, but they are, okay? And that's what we're proving right now. So here is what the result of our proof. What we did is to show that R cross S, the result of the cross product, got transformed to R prime cross S prime in this result. See, R transforms to R prime, S transforms to S prime, and then R cross S equal to T, and turns out the results are also transformed. T, that is T, got transformed to T prime, and T prime happened to be equal to R prime cross S prime. And that's the invariance that we're talking about. That is, in other words, unlike the dot product, right, we have just learned that the dot product, R prime dot S prime, is equal to the good old R dot S. However, R cross S does not equal to R prime cross S prime directly. It only transforms to it, okay, under the rotation system. So that's how it is invariant in that sense. But they are not the same vector. Okay, they only transforms to each other during the rotation. So this is the situation that is to be remembered. However, there is one thing that is the same though, because T is the same as T prime. That means that wait a second, what do I have here? I wrote that wrong. It should be cross. Yeah, what I should have here is that during the transformation of the cross product, this should say R cross S. I'm sorry that this says dot. I copied the wrong thing. Anyway, that is R prime cross S prime is equal to R cross S. The reason is because during transformation, the length, as we learned in the last proof, is invariant. So the vector, once it goes through a transformation, keeps its magnitude is the same. Okay, so that's why the absolute, if you slap absolute value around the cross products transformation, then they are equal, and that is going to be important during the quite a few homework problems. So, yeah, again, remember this is our cross S. Okay, that is the magnitude of our prime cross S prime will be equal to our cross S because one transformed from the other. Okay. And with that, I think that is the end of this section. Now for homework, let's see, yep. So please read all this stuff yourself as well and try to make sense, make sure that everything makes perfect sense to you. Now for homework, we are going to do problems 1, 2, 4, 5, 7, 8, 9, 10. Okay, so please go do your homework, and when you're done, I want to talk about them. So let's look at problem 1 on page 86. Now the problem 1 seems straightforward enough, right? We have the original system where x dot alpha and beta and gamma corresponds to the new components of the new system. And now we want to yank the thing out. That is, express we have the new in terms of the old. Now we want the old in terms of the new. And so how are we going to do that? Well, we're just going to write, I figure, well, how about we just write it out, okay? And I'll let y equal to x primes to be a little less confusing, I think, because you got x and x prime and all that stuff. It gets lost. So I said y equal to x prime and wrote down the 3 components. So by definition, y1 would be the x dot alpha, okay, which is those things added together, and so is y2 and y3. And then we need to solve for x1 in terms of y and the other stuff. So then x1 will be equal to, by Cramer's rule of solving simultaneous equations, we have that determinant divided by the other thing, right, which is alpha, beta, gamma, which happens to be 1 that we showed a little earlier. Or you can prove that very quickly based on their definition. So then similarly, then x2 and x3 have a similar result. But when I looked up the answer in the book gives a very neat answer. Okay, the book says x just equal to those things, and so we have to. So that means I have to work a little harder to make that come out. All right. So then I have it. What is that? So I wrote down the book's answer and see if I can make the 2 answer come together. So by the book's answer, then we have this kind of stuff. Well, x1 will be, of course, alpha 1, y1, and then and is that right? Yeah, I think so. Anyway, let me look at it to refresh my memory. Well, yeah, what else can it be? There's not much worth looking at. Anyway, so I have this stuff, okay? X1 is that. I just wrote that equation, which is a vector equation. I wrote out each component, which is okay. And then I wrote out equation 1 up there, that thing. And then I wrote out x1 and I developed it. That is, I calculated the determinant and wrote it out, which is this thing, okay? By the time you're done with it. And what is that thing? Well, that thing, it had better be, this had better be, what? Why is it not? Give me a second. Okay, I think I got it. There's so many symbols that I sometimes forget what I'm doing. So anyway, so from this equation, I calculated that, I just calculated directly x1 from here. Okay, so then I just developed the determinant, which is, well, then you get y, if you do it y1 along the first column, then you get y1, a bunch of stuff multiplied and subtracted, y2 and y3, etc. So what are those things? Now, I need, this first one is, what is beta, gamma, and all that? So what I did is remember this is one of the given conditions. Alpha is beta cross gamma. Okay, so I actually wrote that out and see what it looks like. So alpha equals to beta cross gamma means by the time I do the cross product, it means that this stuff, beta to beta 2 gamma 3 minus gamma 2 beta 3 equals to alpha 1. Okay, so that thing right here happens to be alpha 1. And similarly, this thing equals to negative beta 1 or something. Is it beta 1? Yeah, I guess. It doesn't, you're not going to get that from here, but it goes by the same pattern because of the way this cross, there are two more cross products, okay? Something about beta is, I don't know, gamma, I mean, yeah, beta is maybe gamma cross alpha or something. Anyway, so everything works out as a result. So this is negative beta 1, and that is gamma 1. And as a result, this equation is the equation, the first equation given by the book. This thing right here. So then that is similarly we can calculate all the other stuff, okay? And that's how the book's answer came out. I didn't write any more because I was totally worn out with all these symbols. So let's just say I'm done, okay? But that is the idea of how to do problem 1, and especially how to get that neat short answer after we get all the determinants out of there. So next, let's consider problem 2, which is more of a number crunching problem. So it makes life, well, it does feel a little better after being stuck in so many symbols in problem 1. And so anyway, for problem 2, we just punch in the numbers. Specifically, we need to verify that alpha equals the beta cross gamma. And so on. And well, I did some dot product here to prove that they are perpendicular, and that should be good enough, okay? And you can also do the other two cross products, that is beta equals to gamma cross alpha or something, and the third one to be sure. And you can also do those things by there's an online cross product calculator. More than one, being the cross product isn't that hard to program. So so that can be done as well, so that we don't have to do number crunching by hand, which is exhausting. And so next, let's look at problem 4, which is orthogonal system. By the way, they are mutually perpendicular. I checked. They are also each have the length of 1, right? And even then, they are not a rotation in the sense we define, because they failed one way. That is, beta cross gamma equals to negative alpha. It does not equal to alpha, which is not acceptable. Therefore, condition 2 on page 84 has failed, and therefore this thing is not a rotation. What it ended up being is it got flipped over. It's a mirror image or something like that, which we will probably do some other time. Okay, there are different kinds of transformation, because transformation isn't just about moving stuff around rigidly or at most rotation. Well, what if you want to flip over or something, like do a mirror image, or even squeeze it? But but for now, we're not going to squeeze it. Okay, squeezing it would not go over well. So next, let's look at problem 5. Okay, problem 5 talks about the axis of rotation. That is, when you rotate something, some points don't move at all. And the reason is because they're right on the axis of rotation, okay? Like a door hinge. The door hinge doesn't move when you close or open the door, because it's the axis for all the turning. So when first I want to talk about what is the angle of rotation. To calculate the angle of rotation, you just find alpha, okay, and dot it with the original x-axis, because the alpha gives the direction of the new x-axis. So then, that is the angle. That is cosine theta equals the alpha dot I. I is the first coordinate, which by the time you get done with that, that would be equal to alpha 1. And in this case, alpha 1, you can calculate it, well, it's given here as 1/3 somewhere. Anyway, I made a mistake here, which is why I'm doing that. Calculate the angle first, but the numbers are given, okay? And you can, but anyway, theta is cosine inverse of 1/3, which is also the answer at the back of the book. So now let's talk about how to calculate the axis of rotation. Let's see. I should just mention that the reason alpha is 1/3 is because in the problem 2 that we're doing, the alpha 1, that is the first component, should be well, right here is 1/3. See, if you put x1, get rid of the 3, put it on the other side. So I think that's how I got alpha equals to 1/3. So continuing talking about problem 5, how to calculate the axis of rotation, where remember if along the axis of rotation it is a fixed point. That is the new x and the old x, that is x prime and x, are exactly the same, which means that we can set x prime equal to x in the 3 equations that we're given. So with that, we can very quickly, being the x prime equal to x, then we quickly come up with these equations, getting rid of the x primes by subtracting or adding them in here. So we got these 3 equations, and then you notice equation 2 and the equation 3 are the same equation. Okay, so we only have 2 equations to work with, and then by the time you do 1 plus 2 or something, you quickly figured out that x2 equal to x3, x1 equal to 0, therefore, which describes a line, which we'll call x2 equal to t, then x3 is also t, and x1 is just 0. So the line 0, t is the axis of rotation for the equations in problem 2. And that's that. Okay, and next let's talk about problem 7, where we're talking about the area of some triangle. Okay, to prove that the area of triangle is invariant, we know that the area of a triangle, of course, is the cross product, right? It's 1/2 the cross product magnitude. Why do I have parentheses there? Let me fix that. So anyways, the area, this is our cross S and the magnitude of it. And since after your transformation, the magnitude of a cross product does not change because the length is invariant. We mentioned that earlier. And as a result, then the area of the triangle, being half of the cross product, will have to be the same. Yeah. And anyway, so next problem 8, I think that is the area of a triangle. What's this? Oh yeah, this is something about, is this an area of a triangle again? Yeah, well, it doesn't matter where the triangle is. The same principle in problem 7 again applies, because the magnitude is invariant. Okay, problem 9, a similar situation. We're calculating the volume of tetrahedron, which is base times height over 3. Base area times height over 3. Now base area is R cross S magnitude over 2. And then the height is T dot R cross S, and then divided by the magnitude. But all this stuff, the magnitudes, right? They stay the same during a rotation transformation. Therefore, which is why the volume does not change during a rotation. So that is problem 9. And finally, problem 10. So problem 10 wants us to prove that the gradient of a scalar function is invariant during rotation. Now first we need to figure out what that means exactly. It just means that the gradient, let's say we have a function, okay? We have a function that is scalar, that has 3 variables, right? It takes a vector and come out, well, it's not really a vector, it just has 3 variables. But anyway, the gradient f is defined as thus, and we'll define it as some point, r1, r2, r3. Now, under the rotation, the gradient function will transform into a different function with different variables. Okay, now it has x prime 1, x1 prime, 2 prime, etc. So then the grad f then is the gradient, the partial derivatives with respect to the new variables, right? At the new point, that is, the point got transformed, the function got somehow transformed, okay? And we'll figure out how the function transforms in a little bit. And when that happens, the gradient invariance means that the old gradient under the transformation will become the new gradient. That is, it's kind of like the cross product. The cross product doesn't necessarily equal to the new cross product, but under the rotation, it does become the new product. So that's how it is invariant. So the gradient works the same way. That is, if we take the old cross product at the old point, and then under the rotation, then the new function at the new point will be once you transform the old one, you will land on the new one, okay, like it's supposed to. Well, that doesn't necessarily work out, but in this case, it does. For gradients, it does. For other functions, something might go wrong in the process of rotation, and stuff is lost, and it can't be the same or something. But we don't care about that right now, because all we need to prove is that the gradient will be invariant in the sense that once it wrote, the old one being go through transformation will be exactly like the new one. Now to prove that, we are going to plug stuff in. Now first from problem 1, okay, where we got that the old x can be written as the new x times each alpha, beta, gamma. Okay, that is the answer of problem 1. So I copy that down here. So g is the f of x, but g is when you plug in the new x into the old f. So that will be the new function g. Okay, that's how we're going to transform g, is just use the old f and plug in new values. And anyway, so we're going to define, in other words, we're going to define g as the function x1 alpha 1, x2 beta 1, and so on. Okay, it has a lot of stuff. It goes all the way down here, but it's the same principle. We're going to plug this. In other words, we're going to plug x as x1 alpha and so on into f to create g. Now, if that is the case, if we calculate the partial derivative of g, let's do x1 first, right? Then we'll end up, after all this stuff, it will end up equal to f1 alpha 1, f2 alpha 2, and f3 alpha 3, which, in other words, this is just multiplication, okay? I don't even know why I wrote parentheses here. This is just simple multiplication. So it's f1 is times alpha 1, and f2 times alpha 2, etc. So in other words, the partial g partial x1 is the same as grad f or del f dot alpha. And similarly, the other two are the same. So partial g partial x2 is del f dot beta, and the third one becomes dot gamma. So then, so what that means is that you notice that del g is equal to del f dot alpha and del f dot beta and del f dot gamma, which is the definition of the rotation. Okay, the rotation says you take the old x and dot each new axis, and that gives you that is the rotation process. And therefore, del f through the rotation does become del g, and that's why we call that, we say that the gradient is invariant under rotation. And that marks the end of this section.